first, let me talk my way through this one. I've got all this stuff down there. You want the internal inductance, external inductance, resistance, and capacitance, and it's a two-wire system. Let me show you. I don't know if I drew a picture on this one or not. No, I guess I didn't. But it's two wires in parallel, and I put down there separated by 50 mils. It's 10 megahertz, and they got a length of 12.7 centimeters, 5 inches, and it's 28 gauge wire. So the first thing I'm going to do coming down here is it's copper too, so it's 5.8 times 10 to the 7th was conductivity. And I think I gave that to you during the exam, right?
Yeah.
All right. So the first thing you have to do is get the skin depth. That's right here, and that's just 1 over the square root of pi times f times mu times sigma, and mu is just mu naught. So that's the skin depth. I think everybody got that right. After you get the skin depth, the next thing you got is the internal inductance, right? And that's the DC internal inductance for the length for one wire. Remember that, that's just one wire. And this is going to be for 2 wires. This is the high frequency inductance. It's the DC inductance times 2 times the skin depth over the radius of the wire, and then it's times the length, right? Now remember, the inductance is eternal, so it's up one, down the other, because it's differential. Some people forgot to multiply it by 2. When you do that, down here is the work for it, but then you'll find the internal inductance is 3.318 nanohenries, and that's based on this calculation and this. And this is just 2 times the skin depth divided by the radius times the DC inductance. Now other people remember the formula where it's all condensed into one. Either one's fine, but you had to remember to multiply by 2. Next is the external. Well, the external inductance, you can go by calculating the B field, then integrate the B field over the area between the two, right? And then once you do, that's the flux, and divide the flux by the actual current. Now remember, the flux caused by one wire integrated over that is the same thing as the flux caused by the other wire integrated over that, due to arguments of symmetry. And what it comes down to, you got to remember this though, your range goes from the radius of the wire to, and then it's going to be the actual separation distance minus A. Follow me on that? Some people they didn't subtract the A from the second part. They didn't take separation distance minus A, and in some cases it doesn't matter. This one it kind of did. There was about I think a 5 to 8% error. Right? So that's right here. That's the external inductance. You all see this right here? After the external inductance, gotta get the resistance, and the resistance. Now remember, it's not one wire, it's 2. It's in differential mode, so it's up one, down the other. So the resistance is the length, which is 2 times the length of one wire, over 2 pi skin depth times the actual perimeter, right? I mean times the radius, right? And the radius of the wire. Everybody understand? I'll post these. Okay. All right. Is everybody okay with that? Yeah. All right. And that's this one. And then finally the capacitance. And the capacitance, I'll tell you a trick on this one. The capacitance is right here. You can go ahead and put a charge on one wire. Let me just tell you the fundamental way to do it. You put a charge on one wire, you get the electric field from one wire. It's rho L over 2 pi epsilon naught rho, right? After that, you would integrate that electric field between the radius of the first wire out to the second wire's separation distance minus the radius of the wire, right? And in that case, you get a natural log integral that has has a separation distance minus the radius over the radius. That's what happens there. And then it's going to be times the constants, and then you get basically the capacitance is charge divided by voltage. Now you can do it that way, right? One person had it inverted, I think, had voltage over charge. But that's the capacitance. And if you want me to, I can work all these things in detail for you, but I think you know how to do this. So anybody, if you want me to work the whole thing out, every detail of it, I will. But that's what it comes down to for capacitance. Remember, the capacitance doesn't matter. You don't have to multiply by 2, and you don't have to multiply the external inductance by 2. But the internal inductance and the internal resistance you have, or the only resistance. That's the only thing. This is a straightforward problem. I had one just like this given to you. Next one is the clock one. Here, I wanna just tell you this. The first thing you wanna do is take a look at the source and find and sketch what the thing looks like. I'm almost reluctant to do this, but I'll try. If it doesn't work, it's not for lack of trying. So, in this case, when we do the typical sketch here, this is 20 times the log of 2 times the magnitude A times the duty cycle here. Well, duty cycle is 50%, so that and the 2 cancel and you get A there, just the magnitude. It's divided by 10 to the minus 6 because it's going to be in dB microvolts. Right now, let me see if I can write this down. Well, I've actually had it here. So that's what it comes in as, and it stays there. I think that's about 133 point something. 3 dB microvolts, isn't it, class?
Yes, sir.
It keeps going, and the first break frequency it hits, this is right for the source, is going to be at 1 over pi tau. And tau is equal to the period divided by 2, and the period is 1 over the resonant frequency. All right? Or I mean, the fundamental frequency. That's 1 over 10 meg, right?
Yes.
So if it's 1 over 10 meg, this is 10 to the 7th and 10 to the 7th by 2. I don't know how come that does that stuff. 10 to the 7th by 2 is going to be 5 times 10 to the minus 8, right? So this tau is 5 times 10 to the minus 8. Pardon? That's the first break frequency. Now it starts coming down at minus 20 dB per decade, right here, until it hits the second break frequency, and that's 1 over pi tau rise. Now tau rise is given as 20 nanoseconds, right? So this is the first, let me just show you what the break frequencies are. Where is that? The low frequency, the first break is 6.366 meg, and the high frequency, where is that? Do I not have it there? I think it's 13. I'm looking for it. This 1 over pi tau rise. Oh, this is it. 15.92. Follow me? Now, if you have that, and then finally, I wanted the value out at the 12th harmonic. So if the fundamental is 10 megahertz, the 12th harmonic would be 120 megahertz. Okay. So that means when I do this, I start here, and this is basically a cookbook. Here's my first thing. That's where I start. Then I have to subtract off the 20 dB per decade losses. That's going from the first to the second break frequency. Then the 40 dB losses, 40 dB per decade from the frequency you end up at, which is 120 megahertz, divided by the 15 point, whatever it was, megahertz high frequency. And then I have to go ahead and add in the effects of the filter. And the filter in this case, H, was equal to 1 over J omega times R times C. It's really, this impedance here is just 1 over J omega C, right? And it's divided by this plus, well, it's really 1 over J omega C over. Oh boy. This is this times, this is the ratio, this would be this, right? Yeah. Times V source is equal to V out. And so V out over V source is, that would be H. Do you agree with me, class? Mm-hmm. And when you do that, let's see, that's going to be multiply top and bottom by J omega C, and you get 1 over 1 plus J omega RC, and this is dominant, I believe. It's much, much greater than 1. So it's really approximated as just 1 over omega RC as the magnitude. If you use that, you can use the whole one. And when you do that, then you get this. This is equal to about minus 14.5.
Yep.
And you subtract that, bottom line, when all is said and done, you're gonna get a value of about 76.47 dB microvolts, right? And that was a cookbook problem. Anybody have any questions to that? If you want me to expand on any part of this, please let me know. I'm sorry it's kind of messy. I do not write as well as Dr. New does. I know that partly because I can't get situated. The next one was this, and this is right from his book. I don't know if I assigned this problem or not, to be honest with you. I assigned a bunch of problems, and this may have been one I assigned.
It was.
Which is fine with me. All right. So for this one, they have 80 plus J50 here, and then it's in a 50 ohm line, so that means Z normalized here, Z load normalized, would be 80 minus J50 over 50. So that's 1.6 minus J1. You got me on what's going on, fellas. So anyway, that's going to be inside the rotated ones, or inside the one circle. So that means no matter what I add to that, I can never get to the article 1 circle. So I have to go from there into the admittance domain, 1 over that. Then I have to put something in shunt with its capacitor. Do y'all agree with me? And the capacitance has to take that from here, the admittance domain, to here. And that's where these calculations are shown, that you gotta add J20 or J.22 to it to actually get to the rim of a rotated 1 circle. Do y'all see this, class? And that means the value of the capacitance that would do that would be J omega C Z naught is equal to J.22, or that C is 0.22 over 2 pi F 1 gigahertz times 50, or 0.7 picofarads. I think a lot of people got this right. A couple people drew it backwards. They had the right values, they just drew the thing backwards. After that, now that you're at this point, now you have to go back to the impedance domain, take 1 over that. And then you see that the value here has an imaginary part of J1.1. Are you with me? So I have to add an impedance that's, minus J1.1, it's minus part. So you have to add plus J1.1, and that's going to be an inductor in series. And so J1.1 is equal to J omega L divided by Z naught. That's just normalization of the impedance. And you calculate L, and L is 8.7 nanohenries. Okay. Then the last one, this is the common mode thing. So because the currents are differential, right? That means I'm in the differential mode, or the impedance of this is simply going to be of that element. It can be drawn like this. This would be J omega L minus M, J omega L minus M, and then the load, R. So that this, if you have a sign, I only wanted magnitude, so I didn't care about the phase angle, but this is a sine, and if you think about a sine, if I want to put it in phasor domain, this would be equal to 10 at an angle of minus 90, but it doesn't matter what degrees it is in this case. I just wanted magnitude on this one. So my V out right here, plus the minus V out, since it's just magnitude I care about, that's going to be magnitude of V in, or 10 times, and then it's going to be R over, and it's the magnitude of R plus, and it's twice this, 2 times J omega L minus M. And sorry it's messy like that. And so this is what this reflects. 10 times R over R plus J2 omega L minus M. L is just equal to 2 pi F, and F is given as 200 megahertz, and that's what you get for V out and magnitude. That's all I needed for that one. All right. So that's it in a nutshell. Are there any questions? That was probably a very easy exam for most of you, and I'm going to say a lot of the mistakes were probably silly in nature or oversights. All right, now, since this is class before the last class, I'm going to tell you that we've covered about everything we need to cover. I'm going to go through circulators, and I can try this down here. I'm not a fan of this, but I'll try it one time. Bear with me. I think I'm going to try it one time. Wait a second. I might have something. There's usually paper under here. Today there is. No, hold on. I'll go with you. No, I want to try it one time.
I got a couple sheets.
I'll see how my back holds on. The only time I use this really is when I was teaching circuits. Circuits, you can do that, you can use this. There's usually tons of paper. This is the first of this class. All right, so the final thing we're going to talk about here, and you've got your book with you, they're going to be circulators and couplets. So here's what a circulator looks like. They're going to have basically a ring like this. If you can tell me the page number, I'd appreciate it.
568.
Page 568. So this is port 1, this is port 2. This is port 3. And here's what the circulator does. But this is sort of a roundabout for electromagnetic energy. It says anything coming in here, it wants to be shunted and comes out there. That's the ideal. It like all the signal that comes in port 1 to be shunted out port 2. But it wants anything coming in port 2 to be shunted out port 3. And anything that comes in port 3 to come out port 1. You all follow me on this? Now, why is that important? Because in radar, what we have is this. We have an antenna out here. And the antenna has input power coming in here that goes out to the antenna for radar and is launched. Then the reflected signal comes back and it comes here and it's shunted to port 3 for processing. And this thing isolates the transmitted and the received fields. You follow me in this? Because if all of a sudden the power at this power level shunted into here, it got sucked into here, it would destroy the electronics of the receiver. Follow me on that, guys? Now, a question, a genuinely decent question is, well, how does a circulator do that? And I don't know all the details, but what they have are ferrite materials that have signal coming in one way will always bend in a certain direction. Signal coming the other way will be shunted the other way. All right, now think about this. You know how when you took, I guess it was EMAG 1, you learned that the charge, the force on a charge caused by a magnetic field was QV cross B, right? And it always did what? It caused the charge to bend one way, correct, class? So if you have currents in these, just go with me on this one. If you have currents / fields in these ferrite materials, if they're going one way, they bend in a certain direction, and another way, they bend in the opposite. That's how a circulator does it, but I don't know, to be honest with you, I don't know the details of exactly how those materials are housed in there, because I've never torn one apart, and I've never really built one. I'm just going to tell you that's how it works, and it's based on the same principle of why charge in one direction bends one way, and charge in the other direction, the magnetic field would bend the opposite way. Now, back to this circulator. So this is port 1, 2, and 3. That means we have a 3-port system. That means we have V1 minus, V2 minus, V3 minus here. And that's equal to this big matrix. This is S11, S12, S13, S21, S22, S23, S31, S32, S33. Now the only ones that they want to be non-zero are the ones that couple signal. And if you look at this, for S, or for V2 right here, let me go ahead and draw this S matrix so you'll see. When I look at this, I have V2 here, right? And I know V2 coming out, right here, that would be in the V2 negative and V2 minus, right? Only comes from port 1. So I look at S21, and that's going to be 1, ideally. Follow me? Everybody? And that should be in there. You see the page in the book where he gives the S parameters for the circulator? What page is it on?
569.
All right, that's a 1. Now, what about this one? From port 2, coming in from port 2. Remember, this has the V1 plus, V2 plus, and V3 plus on this side. So it's going to be row column multiplication, right? So now when I look at V3, that's down here, caused by incoming to port 2, so that would be this one, and that would be 1 as well. Y'all follow me? This is how you fill these things up. Class, you with me on this? Then you have the final one, and that's on port 1 coming from port 3. Here's port 1 coming from port 3, S13, and that's 1 as well. And everything else ideally would be 0. Now, I don't know if Wentworth's book has all zeros there.
You put ones in those three spots.
568.
Yeah, and that's the ideal. Now the real. In truth, you can never get this, or this, or this, usually. You can't get 0. And normally how they measure these are in dB, but you can get a factor of 1/10,000th, or 100,000th, or 1 millionth. And that's like, if you think about in dB, 1,000 is 30 dB, 10,000 is 40 dB, 100,000 is 50 dB, 60 dB is going to be 1 million. Usually 60 dB to 100 dB of isolation between these ports, meaning this. The signal comes in port 1, you want less than 1 millionth, or probably less than 10 million or 100 million of that signal strength to come over here, of the power. So what they try to do is make sure that some of this signal can't go back in. It'll destroy the amplifier if you're not careful. And they probably have additional switching that literally takes this port offline when they're transmitting this signal. It's very fast, because that can destroy it, but they still have circulators. The other thing is that, you don't want anything like when the incoming signal comes back, it does no good if it goes this way. They want all the power to go that way. I'm speaking just from a radar perspective. And to be honest with you, this part right here, the 1-3 coupling, I don't care about in radar. I only care about my signal going out one way, anything coming back from the antenna goes the other way for training. But for other work, they probably will have an application for that. I don't. And I could see in a bistatic radar that there might be an application for that. But that's a circulator in a nutshell. Now, I can only speak of what I know personally, and that's used for radar work all the time. And it's used for probably a lot of communication work anytime you're going to have transmit, receive. You want to transmit, you want all the power into the antenna. Receive, you want all the signal coming back to you to be shunted into the receiver and not into the power amplifier. And that's, in a nutshell, what it is. Now that's a 3-port system. There's also, if you look in there, there's going to be a 4-port system. And usually, I think it looks like this. You could draw these different ways. In his book, he has a square like that. And what is this 4-port? And
Is that for the couplers?
yeah, this is a coupler, and I'm going to tell you this. He should have something where, in his book, he'll have something like this. He'll have a direct, that's the throughput, and then, yeah, you guys 1, 2, 3, and then 4. All right, so that's 1, 2, 3, 4. Is that the numbering in your book, guys?
1, 2,
Yeah.
3.
And it doesn't matter how the numbering is. Really, there's going to be 1, 4 on one side, 2, 3 on the other. It doesn't matter if the 2's up here and the 3's down here. But here's the idea. You want all the signal from port 1 to get to port 2. But you only want a small amount of that signal to get to port 3. And that's really for things like synchronization and stuff. So it might have maybe a 30 dB, maybe 40 dB of loss here. You don't want much signal going here, but you want enough signal there so they can do synchronization work and other stuff. This is, you know what phase lock loops are? All right, well, anything that needs close synchronization, they can peel off some of that signal. Now this is called the isolation port, port 4. And the isolation port usually is not useful for anything. It's almost like this is a 3-port device, only instead of being a circulator, it's a coupler, because most of the signal goes from port 1 to port 2, but some of it's shunted off, so you get maybe 30 dB to 60 dB of attenuation. You have enough of that signal there for synchronization work, things like that. And then there's a dead port there. If you look there, he calls it the isolation port, doesn't he? It's really, isolation means you don't want nothing there. But, you know, I could foresee a point where maybe they want 30 dB of shunt to here of loss, and maybe 60 dB here for some other reason. I can't think of one right now, but I know that there's some weird things. Now, these are only the couplers and the circulators that are talked about by Dr. Wimple. I want to add one other thing. A lot of times, you may need a 5 or 6 port system, and let me tell you why. So suppose I have an array of antennas, all right? And what I want to do is I want signal coming from, say I have 2 sets of antennas I've got. An array here for transmit, an array over here to receive. So I want to have all the power that's coming in port 1 to radiate into the array in port 3. And then I'm going to take the signal that's being received by this set of antenna to come back and on that antenna, and it's going to come in and circulate to a different port. But any signal that's coming back here, it's going to, boy, it's not coming out. It's going to be shunted to a different place. And here's why they do this. You know what bistatic radar is? All right, bistatic means this, in a simple sense. I transmit here, I listen here. Bistatic is very powerful. It's much more powerful than monostatic, but it's much more complicated and much more expensive. Now here's the deal with this. If I'm just here and I transmit and receive, right? Think of radar like light, all right? Now stealth does this. It takes a mirror and it reflects the signal straight up, so nothing comes back to me. So now I can't see anything, because literally all the radar energy is reflected in directions that the receiver isn't. That's how stealth technology works, first order. There's also absorbing stealth, but that's more complicated, and there's no perfect absorbing stealth. It doesn't really work that well. It works to a degree. Now, but how could I, remember that the mirror business is not exact, because the surface is mirror-like. It reflects energy. It reflects energy in a lot of directions, but not back to the sender, all right? Now, with bistatic radar, they have a transmitter here that illuminates space, and the reflected signal, if it's stealth, never gets back there. But some of it gets all over the place. It's scattered on the ground. So now they put receivers, not just one, a lot of times 20 or 30 different receivers. And those receivers, as they receive things, are going to be a long way away. And they want that signal to come back to the primary radar at speed of light limited, and then go through signal processing. So from one of them, they want it to circulate into one bank. From another signal, they want to circulate that information to another, basically I say the bank, but another portion of the receiver, so they can data process this. And here's the deal. They know the time delay from the time signal gets there back that it takes to here. But because they know the path from when the signal sent, speed of light, c times t1 would be when it hits here, right? Then c times t2 would be actually when it gets back here. That means total path traveled would be c t1, t2, right? Now, you know what triangulation is. If they have a bistatic case and they've got one distant receiver, another distant receiver, now they're basically going to, and you're going to get some back here at the actual receiver, you're going to have 3 points. You could put a third one out there, and now you can triangulate and get basically just listening. You can find out where the exact position of the object that caused a scatter. And that's why I'm telling you guys, because some of you probably get into radar. With standard radars that are used by most militaries in the field, they're monostatic. And stealth technology is a nightmare to them. Stealth planes, the 35, F-35, the F-111, I don't know if you remember, F-117 was the first stealth fighter we had. They reflect all the radar energy, every direction except back at, actually most of it's directed up, back at the transmitter. So they're invisible. You can't see them with radars. Matter of fact, when they talk about how big it looks electrically, their cross section is less than a seagull. And you can't see a seagull with a radar at 10 miles, I guarantee you that. And they're even smaller than that. So the first Gulf War, what happened was, when they were doing this with radar, the British had in the field bistatic radar, and they could see our stealth planes. And they'd even call in and say, is that your aircraft? I've been told this. I wasn't there. And I said, how do you know? Because they had set up a bistatic out there that we didn't know about. Well, don't tell anybody, basically, because we don't want anybody to know. There's a lot more to bistatic, but the real thing they'll have maybe 5 or 6 different sets of antennas out there, and all that information is coming back to the primary radar, either through a direct link, like a cabling, or it's microwave dish linked to it. And then that signal has to go through a circulator usually, and it may have 5 or 6 different ports, or even more. So remember, 4 ports isn't the limit to these things. These devices can have 30 ports. Think about roundabouts. They usually have 4 inputs, 4 outputs, right? For a standard car roundabout. Isn't that right?
Yes, sir.
Usually, if you go up to the mall, up to Tiger Town, you'll see they got 1 round. Well, if you go to other places, not down here, you'll see roundabouts that have 10 inputs, 10 outputs, and that's sort of like with circulators too, as well as couplers. There's all sorts of different types. This just gives you a general background. Now, that's as far as I plan on going with this. This is how it usually stops right here. I'm going to mention one other thing. I'm sorry, I didn't bring my book down. He'll go and he'll show you how some lithography, and he'll talk about filters. The reason I don't spend much time on this is you've had filters 5 or 6 different times by now, right? You've had low pass, high pass, band stop. You got filters in circuits, correct? You got filters in signals and systems, correct? You're going to get filters in a couple other classes. I know you're probably your analog electronics that went through filters there.
Yes.
So this section is very redundant. All right, I don't bother with filters here. And the lithography to make this stuff that he has there for the different things, really there's more to this, a lot more. A lot of these things are far more complicated, so I'm not going to do it. That's where we stop this course at. Now, do you have any questions for me? Because what the final is going to contain is everything we've covered from chapter 6 onward. And the final is predictable. Hint, if you look at the homework, you can predict what's on the final, and I mean that sincerely. If you want me to keep going with some new material, I'll do something different than this, but this is your option. No, I'm being honest with you, and if you want me to answer some questions about anything, yes, sir.
When is the final?
Yeah, we can know.
Well, we can't really deal with this until he's here, right? I mean, because then he won't know. It has to be unanimous. Follow me? I guess I could email him, but.
He still has to take that test. The test.
Yeah, I know, and I'm thinking about first he's got to get well. If he's really sick, I just wish him the best. Has anybody talked to him? He sent me a message. He is very ill, and I don't know what very ill means, because I mean, there's appendicitis where you have an appendectomy. That's a lot different than a bad cold. And I've had people that have had all car crashes. You don't know, so I don't know what his story is, but I'll have to find out before. So we really should do this Friday. Do you have a preferred time? Anybody?
I think our people were saying Monday.
We can do it Monday if he agrees. I can't do this unless it's unanimous. What time Monday?
10?
Yeah, 10.
All right, now I don't know if this room's open. Are you free at 10? Is anybody not free at 10 o'clock on Monday? Are you okay with this? I mean, if you are not, then tell me. Because if anybody has any problems with what I'm doing here, just tell me and we'll get the final when is it scheduled?
Wednesday.
At what?
Or sometime.
I mean, I will put it Wednesday in the afternoon if you want it there. But if everybody wants to move it to a different time, then we can do it. You got a problem with the Monday or not? Does anybody have a problem with Monday at 10?
My only problem, I have an online class that I'm taking in Dothan, and I have to drive and take that final either this Friday or next Monday. So if we do it on Monday, I won't be able to come to class on Friday because I'll have to drive and take that final
This Friday.
this Friday.
Well, you got that. Right?
Yeah.
I'm just going over Is,
Yeah, that'll be fine.
I mean, the only thing I'm gonna do on Friday, right now, is go do a summary and answer any questions you have, any problems you want me to work, anything at all, then we'll take care of it then. And in the past, what I would do at this point, I would go ahead into another section of like electromagnetic compatibility that isn't covered in there, or I'd go and extend the radar portion of this or something. But really, that's not part of this course formally, so I'm not gonna do it this time, especially in the summer. Is there, now I got, let's see, in the spring I have the radar elective. If you're interested in, now with radar, they're getting into these things that, it's basically turning into signal processing, and artificial intelligence or machine learning is now becoming an integral part of radar, and here's why. I'll just tell you this. There's so much happening right now. You know, drones are driving a lot of things right now. Everybody wants to be the first to get at really creating drones inexpensively that are very safe to use and are almost something with a brain, something that can make decisions in a way that they can learn to make decisions. Now, machine learning is this, the device actually learns based on situational stuff how to behave. That's what we are. I mean, we learn. Well, radars are the same way. Well, let me just tell you this. First radar is basically, the very early radars, they blasted a huge amount of electromagnetic energy out in the air, and they just listen, and just like your voice when you listen for an echo. Then they got more sophisticated where they start sending many, many pulses of electromagnetic energy, and as the energy comes back, they took all the pulses and they did this in what's called a coherent processing way, where the signal strength increases but the noise will basically not. So they can pull signal out of noise without going into too much detail. Then they got into radars that not only that, but are very sensitive to direction, and you can't really effectively jam them and stuff. That's bistatic radars. And then they get into I'll spend too much time getting into every type of radar. There's search radars, which searching an area. Then there's tracking radars that locate a plane, and once they see it, they lock on, and they're all, that's what you see in a lot of these movies where you hear they got a radar lock. I mean, you're basically dead at that point. There's nothing, if you're a pilot, unless you've got a lot of flares to drop. And even then you're probably dead anyway, because a radar lock's different than something that's going after the thermal signature. That means you need a big chunk of mass falling out of the back end, or a lot of chaff. That's just flaked aluminum, so it looks like the big radar signature, because these devices fly at the major signatures, either thermal, that's why they drop flares, or chaff that looks like a lot of metal. Well, now radars, the problem with radar is when you're using a radar, you're exposing yourself. Everybody knows you're there. And guess what? They have missiles that home in on your radars. They're anti-radar missiles, and they're very effective. And that's why, and when you get into, over in the Gulf, for instance, when they have these Russian radars, these aren't really sophisticated radars. They flip the switch and fire the anti-radar missiles and blow them all up. And so they don't have radar there. And that's what happens left and right. When you turn on a radar, you're really exposing yourself. So now they get a thing called passive radars. And passive radar does this. It uses electromagnetic signatures in the area, for instance, TVs, radio stations. But this takes machine learning, and it has to learn if that signal is being transmitted over there. It has to know exactly the signature of that signal, all right? And there's ways to do this. Then it can say, I don't have to send anything. I'm just going to listen. And because that is sending it, I can act like a third leg in the third leg in a bistatic radar. Now, passive radars, like that, require a lot of machine learning. And it takes, for a given region, remember, you can't just create one and say, it's going to know what to do if I put it in New York City or Baltimore or Iraq. Because all the different electromagnetic sources are different, right? So what it has to do, it has to learn what the signature of the electromagnetic signature is that they would receive reflected is from different type of planes and missiles, and they do this sometimes by simulation, but most of the time they do it by literally taking, they're just simulators of targets out there. They have inflatable structures and things like that that look just like a MiG-21 or something like that, and they'll take them around, and then that thing will learn what the signature will be that it receives back.
And that is a very interesting type of radar that a lot of the drone technologies are interested in, because it doesn't require them to have an active transmitter. Matter of fact, there's things where they would like to put a transmitter, radar transmitters at given points all throughout an area where drone deliveries, and then those things could reflect the energy, and the drone with enough sophistication would be able to figure out where the actual thing is that's reflecting. And here's the real thing. Now, we are like radar in some ways, our brain. We don't transmit anything, right? But if I look around this room, I can see clearly the delineation. I know that's an exit sign. I look at the back there, it's an exit sign. I can tell the difference between this table, right? Because of color and density, but I've trained my brain to distinguish these electromagnetics, this signature in my brain, my eyeballs see, and that's where they're going with radar. They want to get a radar that's going to be just like you at a much lower frequency, where it doesn't need any kind of source to transmit from. The only thing it's going to do is receive, and because it'll have binocular-like vision, it means it has to have two antennas, at least binocular. It might have several others. It can figure out in the environment, and it can figure out something effectively like color. It can figure out texture. It can figure out surface roughness and all that stuff. And that's where we're going with this. But I tell you, that requires a very sophisticated type of machine learning for a device. And there's more to this, but the one animal that does this the best is a bat. It doesn't use electromagnetics, but I mean, as far as an interrogating environment, it does transmit a signal. But bats are amazing as far as their ability to discern everything in their proximity and know both texture and range, and they're just amazing. Dolphins, I guess, to some extent too, but bats are unbelievable as far as their data processing. We'd like to have a drone technology with something like that if it had to have an onboard transmitter. I mean, a lot of people would like that. Or we'd like passive radars, but that might be another generation. It may be when you guys are probably, I don't know, having your kids go to first grade, that's where this stuff is going to start coming into being. Because in 10 years from now, most of you will be married with kids, believe it or not. Statistically, I believe I'm speaking the truth. Anybody married right now here? No?
Getting engaged next week.
All right, well, then you'll probably have the first one out of the chute. I'm not kidding, man. I've been here for, I've been here 34 years, going on 34, and I have seen kids that I taught, their kids, and now their kids are getting old enough to have kids. And I mean, they're getting right there, and I can't tell you how weird it feels. Time flies. It seems like only yesterday I was talking to somebody about, I don't know, electromagnetics or something like that, and going out and playing pool with them or something. Now they're going to be a grandfather. It's weird. Anyway, you don't have to hang around. I'm basically done unless you want me to do problems or something like that. You guys can think of. You okay with that test? You here?
Yeah.
I can tell you if you want.
Yeah, for whatever
Plus
reason.
10, I'm pretty sure. Like, you take your grade and have whatever it is out of 100 and add 10.
That's 2.5, that's right. And I'm not going to worry about the circulator and upper homeworks. So all the homework we've got has been given already.
Alright, so don't worry about any of this stuff.
No, I'm not going to, no, I just want to make that known to you.
Okay.
Where's my line? He will get over it.
So just add 10 to whatever the score was.
Percentage.
Yeah, like out of 100.
You're getting engaged, you got the ring already?
Oh, yeah.
You gonna have a little treasure hunt for it?
Nah, I'm gonna do it old school, just come out and ask her.
Well, she's probably ready to make the decision.
We've been together about almost 5 years, so.
Yeah, that's the time things seal up.
The funny thing is, my wife's got an engagement ring, she'll never wear it again.